When you look up at the moon, you're looking at a history book. Its surface is this incredible record, written in dust and craters, telling a story of a really violent, fiery past. But to actually read that story, you need to understand its chemical language. And that's where our hunt begins, for one crucial, but, as it turns out, incredibly shy piece of the lunar puzzle.
For decades, we've been trying to map out the moon's chemistry from orbit, to figure out, how it all came to be. But what if there's a huge part of that story that we just couldn't see? It turns out, one key ingredient that holds the secrets to the moon's entire volcanic history has been hiding in plain sight. And finding it, well, that's been a massive challenge.
And that missing ingredient is silica, or SiO2. Just think of it as the master key to all of lunar geology. Seriously, the amount of silica in any given rock tells you pretty much everything about the magma it came from. It's basically a chemical fingerprint for how the moon's crust was built. But here's the problem.
When you look up at the moon, you're looking at a history book. Its surface is this incredible record, written in dust and craters, telling a story of a really violent, fiery past. But to actually read that story, you need to understand its chemical language. And that's where our hunt begins, for one crucial, but, as it turns out, incredibly shy piece of the lunar puzzle.
For decades, we've been trying to map out the moon's chemistry from orbit, to figure out, how it all came to be. But what if there's a huge part of that story that we just couldn't see? It turns out, one key ingredient that holds the secrets to the moon's entire volcanic history has been hiding in plain sight. And finding it, well, that's been a massive challenge.
And that missing ingredient is silica, or SiO2. Just think of it as the master key to all of lunar geology. Seriously, the amount of silica in any given rock tells you pretty much everything about the magma it came from. It's basically a chemical fingerprint for how the moon's crust was built. But here's the problem. For something so important, silica is unbelievably hard to spot from space.
So why can't we just point our fancy instruments at the moon and find the stuff? Well, as it turns out, silica is a master of disguise, and the universe has been working for billions of years to keep its identity a secret.
Okay, so the problem is really twofold. First, silica's own light signature is just kind of complicated. But the real issue is something called space weathering. For billions of years, the moon has been blasted by micrometeorites and solar wind, and that process creates this glassy coating on all the rock grains. It's kind of like trying to read a sign that's been sandblasted for centuries. The original message gets all blurred and hidden away.
And because of all those challenges, this is what we had to work with. On the left, that was our best global map of silica, from way back in the late 90s. And the resolution? About 2 degrees per pixel. We're talking a single pixel covering a block dozens of miles wide. The goal on the right was to get something so much sharper. A map that could take us from that blurry, fuzzy understanding to a totally crystal clear picture of the whole moon.
To get that picture, scientists knew they needed a brand new approach. They needed better eyes, a secret clue that even silica couldn't hide, and a detective that was smart enough to put all the pieces together. They needed an AI.
So the toolkit they put together had 3 key parts. First, better eyes. They used amazing high-resolution data from Japan's Kaguya orbiter. Step 2, a hidden clue. This is the secret weapon. It's called the Christiansen feature. It's this unique little quirk in the infrared spectrum that's super sensitive to silica. And step 3, the smart detective, a special type of AI trained to spot that hidden clue even through all the noise.
So how does this AI detective even work? Well, you can think of it as having a whole bunch of special filters. Each one is trained to look for a very specific, very subtle pattern in the light bouncing off the moon. And by combining everything that all these filters see, the AI can spot these complex relationships that are totally invisible to a human eye, patterns that scream silica. But here's the thing about an AI. It's only as smart as the data you train it on. To really get good at its job, it needed to study real lunar samples. And that's where the brand new samples from the Chang'e 6 mission became the absolute key witness. We're talking about the first rocks ever brought back from the moon's far side. They provided the ground truth the AI needed to really learn what it was looking for.
All right, so with this super-powered toolkit and brand new, one-of-a-kind samples from the far side, what did the AI find? It didn't just find some silica. It revealed a completely new picture of the moon.
And here it is. Just look at that. For the very first time, we are seeing the moon's silica distribution in absolutely stunning detail. The blue areas, low in silica, are those vast volcanic plains we call Maria. And the warmer, reddish tones? Those highlight the ancient Silica-Rich Highlands. The level of detail here is it's breathtaking. We're seeing things we have never, ever seen this clearly before.
So how good is it, really? Well, the model's predictions match the actual silica content of the real moon rocks with an accuracy of 97.5%. That is an incredible number. It's a massive confirmation that this new method isn't just working, it's working exceptionally well.
But what truly makes this map a game changer is the resolution. Remember that old map where a pixel was miles across? This new one has a resolution of 59 times parsecs per pixel. It's like going from a blurry satellite photo of an entire state to being able to see individual houses. This is a revolutionary leap in how we see the moon's geology.
So what stories is this incredible new map telling us? Well, the first one is a tale of two moons. It confirms, in beautiful detail, a huge chemical difference between the side we always see and the far side. The volcanic plains on the far side are consistently higher in silica. That suggests the magma there evolved differently, probably because it had to push through a much thicker crust to get to the surface. The second story reveals this really strange pattern on the near side. In those vast volcanic plains, the silica content isn't random at all. It's lowest near the equator, and then it steadily increases as you move toward the poles. This points to some kind of large-scale process, maybe something to do with the moon's ancient rotation, that sorted the composition of the mantle by latitude. It's kind of weird, right?
And the map is so detailed it can even see different flavors within the maria themselves. So take a look at these two giant lunar seas. They're both low in silica, sure, but the map helps confirm they have totally different chemistries. Mare Tranquillitatis is rich in titanium, while Oceanus Procellarum is low in it. This tells us they were fed by completely separate magmatic plumbing systems deep, deep inside the moon.
So just how much of a difference did those new rocks from the far side really make? Well, after the AI got to study that new data, its predictions changed. A lot. The biggest changes were in those low silica maria. It turns out, adding just a few new rocks helped the AI get way better at identifying those specific volcanic plains all across the entire globe.
Look, this map is a monumental achievement. But like any great discovery, it answers some big questions while uncovering even more fascinating new ones. And its limitations? They actually point us directly toward the moon's next great chapter.
And here are the next big mysteries. These places are some of the most unusual spots on the entire moon. They're sites of a rare, super-evolved, silica-rich kind of volcanism. And in these specific spots, the AI struggles. The map says they're only kinda high in silica, when we know from other data that they should be totally off the chart.
And the reason why is actually pretty simple. These are the model's blind spots. We have never, ever brought back a rock from one of these exotic volcanoes. The AI has never seen a sample of this stuff, so it doesn't really know how to identify it correctly. And this is exactly why future missions are so crucial. NASA's Artemis astronauts are actually scheduled to visit the Gruithuisen domes, one of these exact blind spots, to collect the very samples we need to finally complete the picture.
So, by combining better data, a really clever insight, and the incredible power of AI, we basically created a new lens to read the moon's history. We've solved the missing silica. But in doing so, we've found new mysteries and new questions we didn't even know to ask. The moon is finally showing us its secrets. The only question now is, what will we